This is FRM Part 1, Book 2, Quantitative Analysis, and Chapter 10, Modeling and Forecasting Trends. The good news for you guys is that we're going to build on the linear regression model material that we've discussed over the last couple of chapters. The challenge for you guys is going to be that we're going to add a few more extra issues, extra concerns, extra considerations that we probably didn't need to worry about too much in those previous chapters. So let's get right into the learning objectives. We're going to describe linear and nonlinear trends. We're going to use those trend models to forecast trends. And then from a list of particular models, we're going to try to decide which one is best for our specific problem, including things that we've done before, like the MSE, and things that we haven't done before, like the AIC and the SIC. And then finally, we'll look at some necessary conditions for those models to be consistent. All right, let's start with some description of a trend. And before I get into the slide, I want to go back to something that I learned, I don't know how many years ago. I remember reading in the Wall Street Journal that Walmart's sales from a particular quarter to the next quarter had risen for some incredible number of quarters. I can't remember really the number of those quarters, but it was like, I don't know, it wasn't 10,000 of course, but it was some big number. And I thought, all right, this makes sense if we're going up and up and up and up and up and up. There's a trend. And so can we find a model to predict those same store sales for Walmart? And the answer, of course, is yes. Now, sometimes that trend is going to be linear, so it's going to go up and up and up and up like that, or sometimes it's nonlinear. Sometimes it's going to increase at an increasing rate or increase at a decreasing rate. So I'll show you some of these linear and nonlinear models, and then we'll have to kind of pick which one that we like the best. All right, so notice what I have in that first circle point. It's a pattern of gradual change in a condition, an output, or a process, like sales, like cash flows, maybe dividends, maybe credit ratings. Lots and lots of economic examples that can be applied to trend analysis. Trend forecasting is quantitative, so we need to collect data just like we did back in our regular linear regression analysis. And we're going to use these observed and well-known and verifiable data from history. What we're going to do then is try to use the history to predict the future. Now, the easiest thing to do is just go back to whatever grade that we learned graphs in. So we've got the little graph. And so what we're going to do is on the horizontal axis, we're going to use time in this case. And then on the vertical axis, we're going to use our random variable. Now, the causes of the trend include things like evolving preferences, technologies, institutions, and demographics. I mean, here's a nice little picture of the labor participation rate in the United States over the last, about 10 years. And so note that it had steadily been declining all the way up until, probably 2015, and then it has been steadily increasing. And so what can we say about this trend? Clearly, it was a downward trend that appears to have been reversed. And there are lots of other factors that contribute to that swing from the downward trend to the upward trend. I don't want to get into a dramatic economic or political kind of a conversation here, but over the last couple of years, some things have changed dramatically, and so that might explain why we've had that uptick. Now, the question, of course, is, are these slowly evolving preferences and technologies and institutions and demographics, whatever those variables are they permanent, or is it just a short-term phenomenon? All right, so let's go back to our simple linear regression model where we had an independent variable and a dependent variable. We're going to use that same model here, look at it inside of that blue box, where time is the independent variable, and on the left-hand side of the equal sign is the t variable, which is the trend, which are things like the Walmart sales or credit ratings or whatever variable that you're looking at. And so I want you to think about that time, that independent variable is going to be, it's going to be a 1 and a 2 and a 3 and a 4 all the way out to, however long you can collect the data. The intercept term is still the same intercept term that we've had before, and beta 1 is the slope of the line, which can be positive or negative. So hopefully you get a sense of what we're trying to do here to decide if there is a positive or a negative relationship between the passage of time and the dependent variable. And so there's a quick picture of whether the slope could be upward or downward. Increasing, of course, goes up. Decreasing, of course, goes down. And there's an example in the last square point, sales at Nike products. We probably will see a diagonal line angled upward, indicating that sales are increasing steadily over time. Now, this relationship between time and the dependent variable does not have to be linear. It can be nonlinear. And so there are some good pictures. Increasing at an increasing rate, we are decreasing at a decreasing rate. And then we can have a U-shaped function or an upside down smiley face function. And note, these nonlinear trends are best described by adding another independent variable and then squaring it. So notice on the right-hand side of the equal sign in this regression equation, we have time, and then we have time squared. Now, the interesting thing about this is that adding the time squared variable to the right-hand side of the model might increase its efficiency, it might increase its consistency. And we'll see that as we go through the slide deck. All right, here are 6 different types of models that can be used to describe the relationship between time and that trended variable. Notice that those models that are raised to the 2nd power or the 3rd power, those are nonlinear models. Ones that are not, they remain inside of those linear regression categories. So think about these 6 models right here, and there are others as well. Think about these 6 models, and we're trying to estimate the relationship between time and some dependent variable. We can use software to produce beta 0 and beta 1 and beta 2 and beta 3. If we need to, we can do that really, really quickly. So the question then becomes, which of these models is going to best identify the true relationship between time and the trended model? Now, here's an interesting thing that a variable trend could be nonlinear, but if you take the logarithmic form of it, it could transform it into a linear relationship. And this happens lots of times in economics and financial data. And so what we do, look at the bottom blue box there, we transform that model from just our regular model into the natural log of time. That converts it into a linear model. All right, let's look at fitting these trend models. So for the purposes of estimation, what we're going to do is we're going to fit to data a time series of y to explain past data. We're going to do this the same way we did back in our simple linear and multiple regression discussions. We're going to use a least squares regression. And what we're trying to do is minimize the square of the difference between the actual values and the estimates. And I always give my students the example of the S&P 500 index. You guys are aware that when the S&P 500 index was created back in 1923, it really just followed, just a handful of stocks. But after the Depression and after World War II, sometime in the 50s, I think it was 1957, the number of stocks was increased to its current level of 500. But what they had to do was go all the way back to figure out what it would have been all the way back in 1923 had all those companies been around. And so the S&P 500 index really was kind of based on a value of 100. That's where it started. And so I want you to think about this. So suppose that the last 5 days of the S&P 500 index were, and let's go back in time, say 100, and then 102, and then 104, and then 103, and then 105. Let's just pick those numbers, all right? So we use this least squares regression model. We estimate our set of linear parameters, and let's forget about just 5 observations. Could be 500, but let's just live with just the 5. And let's suppose that we use those models to go back and predict what the model would have thought the S&P 500 would have been in years 1, 2, 3, 4, and 5, right? So started 100. Maybe the first year was 101. Maybe the first year's prediction was exactly what the actual one was. But then in year 2 it was 101.5, and then 102.6, and then 103.8, and 104. Whatever those numbers are. So what we do is we need to take the difference between the actual values and the estimated model values of that S&P 500 index. Then we have to square them. Remember, we have to square to get rid of the negative. And then we kind of do a bunch of stuff like we did back in our simple linear regression and even in our simple stat stuff, where we get some measure of volatility. All right, so the software that we use in these models is very easily going to find the equation such that we're going to solve for the argument that minimizes those least squares, right? So that argument is the argument that minimizes. So think about this. I always tell my students, think about of a vice. You have all this data and you're trying to squeeze the vice down into its minimum range. And that's what you get. And those are theta. That's what that means there in the blue box. So that's the beta 0 and the beta 1 and however many parameters that you have in there. You're trying to squeeze that variability. So here's just a quick slide about what this means, what the software does. So if we have just our regular model that I introduced in one of those very first slides, the software is going to find the equation that minimizes, right? That minimizes the YT. Let's look inside those brackets. YT, that's just the actual value, minus the estimated value, and then you square it, and then you go from t equals 1 all the way to t, and you find beta 0 hat and beta 1 hat that minimizes that relationship. It does the same thing with the nonlinear trend there at the bottom. Now, what about forecasting? So what we're going to try to do here is we're going to use our trend model to predict the value of a series of Y into the future. All right, so think about the Walmart sales or the Nike sales or the S&P 500. Wouldn't it be awesome to be able to know what the S&P 500 index is going to be tomorrow? I assure you that if you knew what the S&P closed at tomorrow at 4 o'clock, that I could turn you into at least a billionaire, if not a trillionaire, depending on what kind of swap contracts we could invest in overnight. All right, so this is really important stuff. So what we're doing is we're going to take our model. There's our model in the first blue box, and then we're going to add an H to it. So the T plus the H is going to be some period in the future. Notice in that second square point I have to forecast the H step ahead value of a series Y. In my S&P 500 example, it sounded perfectly legitimate and reasonable to say, what are we going to do tomorrow? What's that S&P 500 index going to do tomorrow? But if we're looking at things like revenues or cash flows, or maybe operating expenses, maybe we're the operations person in charge of a manufacturing facility and we want to see what those expenses are going to be going forward. It could be 1 month and 2 months and 3 months or 12 months. But remember that when that H gets higher and higher, that model is probably going to be less and less accurate. Now, of course, when you forecast the trend, we automatically assume, just like we did back in linear regression, that that error term has a mean of 0, so it drops out when we're making these forecasts. Now remember, those true parameters, beta 0 and beta 1, are unknown, and the forecast is given by the two betas with a hat on top of them. So those are the least squares estimates, right? The least squares estimates of the true population parameters, which are unknown. Back in my example of the S&P 500 index, we would have no idea what those numbers are in the true sense. I mean, we could try to figure out what they ought to be, but there's no way of knowing what they truly are. So these are estimates. That's why we call them least squares estimates. All right, so here's the question. Let me go back just quickly. Can I scroll all the way back? We have all of these models. So here are 6 of these models. So how are we going to figure out which one fits our data best so that we can make the best prediction? So how can we do this? We're going to use the MSE and we're going to use R square. And there are some other things that we're going to use here in just a second. So let's go back and review what we know about the MSE, the mean square error. It's the average of the sum of the squares of the difference between the actual and the predicted values. All right, so think about my S&P 500 index example, the difference between the actual and the predicted values. It's the average sum of those. Now that MSE is based on the in-sample data. And so that regression model with the smallest MSE is also the model with the smallest sum of the squared residuals. And there's the formula for the MSE. And so that's all we're doing there. Let me just remind you that this mean square error relates to stuff that we talked about before, sum of the squared residuals, remember we had that SSR, and the coefficient of determination, which was R square. And remember, the coefficient of determination was the correlation coefficient times the correlation coefficient. And so there are some good formulas that give you a sense of the relationship between what we're trying to do here and then what we did back in our linear regression discussion. Now, the problem with using the MSE is that it's going to produce a decision that has some bias. All right, so the use of the in-sample MSE to estimate out of sample predictions or future evaluation of that MSE is not going to work because the in-sample MSE cannot increase when more variables are included. So there's going to be a downward bias when predicting the out-of-sample error variance. All right, so MSE has an inherent weakness. So what we can do, right, if you're saying to me, hey, Jim, the problem is in that the in-sample MSE has a fixed number of observations, and therefore it's going to be biased, well, then why don't we just fix it? And of course, we fix that by using degrees of freedom. And now in this context, it's known as the degrees of freedom penalty. And so we're just going to call this S squared, and we're going to adjust the MSE for degrees of freedom. Now, there are other models that do this as well. There's this AIC and the SIC, the Akaike information criterion and the Schwarz information criterion. They're always also known as the penalty factor times the MSE. And so all we're doing here is we're trying to refine our decision making in terms of identifying which model best suits us. And so notice that the penalties occur with kind of like a degrees of freedom. This is a penalty. So notice that the AIC has a different penalty than the SIC. And so those two different ways to evaluate the models are going to help us identify which ones are best. Now let's look at same sample size, a graphical comparison of the AIC and the SIC. And so notice what's happening here. As we move through that horizontal axis from 0 all the way out to 0.35, and then as we move up through time, notice that the adjustment for the simple degrees of freedom, the S square is relatively small. For the AIC, it only rises slowly, but the SIC rises way faster than the other two. So let me go back here. Notice that putting that T in front of the MSE stuff really is a larger penalty. Let's look at an example here. So we've got 60 observations, 6 parameters. We're given the sum of the squared residuals at 785, and we're asked to compute the MSE, the corrected MSE, and then the standard error of the regression. And there are some good formulas that we used earlier in those slides, and so you can easily compute those. How about consistency? There are 2 conditions required for a model selection to be considered consistent. All right, and this is based on whether the true model is included among the regression models being considered. Okay, and that should make perfect sense. All right, two parts here. So the first part, when the true model is one of the defined regression models, then the probability of selecting the true model approaches 100% as the sample size increases. And when the true model is not one of the defined regression models being considered, then the probability of selecting the best approximation model approaches 1 as the sample size increases. All right, so those should make perfect sense there. And that takes us up to the end of this chapter 10. We'll do some seasonality next.